document, right? The CR is present here, Miraj.
Yes, sir.
Did you inform everyone that the class has been shifted?
Yes, sir.
So there is no problem with that, right?
Yes,
The
sir.
shifting of the time actually, taking it almost 45 minutes ahead of the scheduled time. Sorry, there is a meeting at 3. That's why actually I need to reschedule the class. Professor Hassanul Kabir actually was supposed to be present here, but he is on leave. That's why actually I need to represent him. Anyway, let us begin. In the last class, we started counting processes, and we also actually discuss some of the properties of the counting processes, and then actually we started one of the most popular actually counting processes like the Poisson process. And today, actually, we will continue with that. In the last class, we have actually ended here. If you can recall, then actually, the accounting process actually associated in many systems with any systems. And here actually, by the term inter-arrival time, we mean if this is time, the process starts here. This is the first arrival. This is the second arrival. This is the third arrival. So each of the arrows, downward arrows, if it represents an arrival, then we denote this interval starting from the beginning to the first arrival as the first arrival time, and it is T1. Then the gap between the second arrival time and the first arrival time is termed as the interarrival time of the second event. Accordingly, this is the interarrival time of the third event, and you can have interarrival time of the nth event, which actually will be in between n minus 1th arrival and nth arrival. So this one is the interarrival time of the nth event. Our objective is to know the distribution of the random variable Tn. So Tn is the interarrival time in general, where n equal to 1, 2, and so on. Our objective is to know the distribution of the random variable Tn. So Tn, in general, it is for Poisson process, it is exponentially distributed with parameter f. And we discussed this one in the last class, where we actually considered that if T1 is the first arrival time, or more specifically, if we consider the complementary CDF, this says T1 is greater than T. If this is T, that means the first arrival occurs after T. So this oppositely says there is no arrival in between 0 to T. And as you know, the number of arrivals in a Poisson process is represented by Poisson distribution for an interval. So we can see the number of arrivals in between 0 to T with the length of T will be, if it is n, the probability that there are n arrival will be e to the power minus lambda t to the power n or k, whatever, say k factorial, if there are k arrivals. And if we calculate it for 0 arrivals, k equal to 0, then this becomes 1, this becomes 1, and resulting in e to the power minus lambda t. So the complementary CDF for the variable T1 is actually this one. And if we consider the original CDF, then the original CDF of T1 for the value T will be 1 minus e to the power minus lambda t. T is greater than or equal to 0. This represents the CDF for the exponential random variable with parameter lambda. That's why we call that the first arrival time is exponentially distributed. Similarly, the distribution of T2 can be calculated. If we consider T2, then once again, this is time axis from 0. We have first arrival. We assume that the first arrival occurs at S for now. And we want to know what is the probability that the second arrival occur in between S to S plus T. And the time is represented in this way, S to S plus T. That means S is excluding, but T is including. S plus T is including. So here, S actually is part of the first arrival. And after S, we have the interval time for the second arrival. And once again, S plus T is part of the first arrival. So since they are at disjoint time period, so number of arrivals, according to the definition of Poisson process, the number of arrival is independent. And so what we can consider that the number, the T1 here and T2 here should also be independent. If they are independent, and actually they are related to, given that the zero event occurred here, the number of arrival is 0 here, given that the interval is this from S to S plus T, given that the first arrival occurs here. Since the number of arrival is independent at disjoint time period, so these two events are independent. And what we can do, we can remove this, like the probability of A given B. If A and B are independent, then we can write probability of A. Second thing, now the problem becomes the very same as the first one. What is the probability that an event take place in 0 to t, no event? And so this calculated at e to the power minus lambda t. Here we get the same thing. Zero event in the interval s to t, which actually is t. So it will be this one. And accordingly, we can say T2 is also exponentially distributed with rate lambda. And accordingly, we can write Tn following similar speed. We can write that Tn is exponentially distributed with rate lambda, and for this is for n equal to 1, 2, and so on. Not only that, T1, T2, Tn are IIT. So what we can say, the Tn's are IIT. They have the identical distribution and they are independent. This actually definition is required in solving, in modeling many problems. So keep it in your mind that whenever we consider Poisson process, interval times are IIT. And the distribution is exponential with rate lambda. Now, if we move on to the next part, what is the earth arrival time? That means, once again, we consider this is T. We start here, the first arrival occur here, second arrival occur here. Let's say the R number of it. This is first, this is second, and this is R. If this is the R number of arrival, earth arrival, then actually, if we denote it by TR, no, not TR. TR actually, we denoted TR as the interarrival time, but it is not interarrival time. We consider this one starting from the beginning up to the earth arrival. What is the time length? Let's say L denote this one. So L of R, the time that the system requires to have R arrivals. And this one actually is the sum of R interarrival times. Our objective here is to learn the distribution. Anyone can tell what is the distribution of R? All of you know it. Because we have learned it in the fourth semester. Any volunteer here? No. Okay. Then in fourth semester, we learn a random variable named m r long. Can anyone recall how did we define m r long random variable? Actually, an m r long random variable is the sum of m IID exponential random variable. M IID exponential random variable. They have the same parameter and they are independent. So here, if you just focus, then T1, T2, T3 all are exponential with the same parameter lambda and they are independent. So we can say here this LR is also the sum of R IID exponential random variable. So LR is also M R long distributed with parameter R and lambda. The book that we are following, they instead of telling M R long, they are telling it is R R long. If you tell R R long, then actually you do not need the parameter here because the name itself carry the parameter. Anyway, but however you can put it here. Now, what is the distribution of LR? Here actually an explanation is given. What is that? We wanted to know whether the Earth arrival occurs here or not. Whether the Earth arrival occurs here, this duration is a very, very tiny time period, very small time period. It is L and it is L plus del of L. So we want to know whether this very small period of time, the Earth arrival occurs or not. And then this probability is that LR has a value in between L to L plus DL is that R minus 1 packets or R minus 1 arrivals occur during the period 0 to L and a single arrival occurs in the interval tail of L. So the joint probability of these two events actually collectively defines that exactly R packets or R arrivals occur during this interval. And once we have this one, then actually this is same thing. Okay. By applying the Poisson distribution, because the probability that R minus 1 arrival occurs in a period of L is e to the power minus del of L times del of L to the power R minus 1 divided by R minus 1 factorial. What is the probability that exactly one arrival occurs here in the period tail of L? Actually, when we define the Poisson random variable, we define that three quantities. The probability of zero arrival was defined in this way: 1 minus del of lambda of del t plus a very diminishing function that becomes zero quickly when del of t actually just a minute. Sorry, just a minute. I'm actually exchanging one message with the registrar. Just a minute. Sorry for the interruption. Sorry. So the probability of zero arrival is this one. Probability of one arrival is lambda times del of t plus this one, and two arrival is
else.
so, and you can find the mathematical derivation of this one in your book. So one arrival actually occurs with this probability, and this one becomes zero when delta of t is very small. That's why we only consider that the probability of one arrival is this one, lambda times del of L instead of t del of L. And when actually we process this one, then del of L here and here cancel out each other, and we find that the PDF of the Earth arrival time is this one, which actually is the R-long R distributions. Now, a compound Poisson process in the morning session, this took a lot of time. I will be brief here because I think you know everything. What is a compound process? Or more specifically, a compound Poisson process? We tell a stochastic process, a counting process if it counts. So if you consider a stochastic process that counts, become a counting process. A counting process with a specific property that is the independent increment plus stationary increment actually are termed as Poisson process. Also, you can say the a counting process with the number of arrival defined by Poisson random variable is also a Poisson process. Now, this Poisson process actually counts the number of arrivals up to. Let us consider a special type of Poisson process that actually not only counts the number of arrivals, but also it counts one more thing associated with each arrival. There is another counting associated with each arrival. How? The example that is taken from the book at the bottom, see, it is very well defined and well said. Assume students arrive at the university bookstore or library or cafeteria or whatever bookstore, say, to buy books in a Poisson manner. That means we have a Poisson process, say, at the door of the bookstore that counts number of students who enter into the bookstore. So we have the Poisson process. Let's say NT is the Poisson process. It counts number of students arrived. Now, when you have the number of students arrived is NT, then after entering into the bookstore, let's say each of the students buys some books. Now, the number of books that is purchased by each of the student is IIT random variable. This one is important. This random variable should be IIT. Then WI is the random variable representing number of books purchased by the ith student. Then X of t is a compound Poisson process that counts number of total book purchased by the students. So why it is compound? Now this is not a single counting. There are individual counting and you are adding the counted values together. That's why we call such a Poisson process at its core, it is still a Poisson process because it is counting the number of students arrived. But since each of the student is associated with the second counting, then we can have the total number of books bought by all the students, and we call x of t that represents the total number of books as a compound process. Just a minute. That's what the problem with the online classes. Just a minute. Sorry for the interruption once again. So what we have x of t as the total number of books purchased by the group of students, or all the students, not group of students. Let me make one correction. All the students, those enter into the library by time t. So since it's a Poisson process, time should be associated with that. It evolves over time. And from this process, actually, we are interested in knowing two things. One is the expected value of x of t. What are the expected number of books that will be bought by the students by time t? Another one is the variance of that one. Variance of books that will be bought, total books that will be bought by the students by time t. So x of t is a random variable, all of us know. Since it's a process, a stochastic process, so it's for different values of t, actually we will have random variables. To calculate these two quantities, actually the book uses some sort of transformations, but we will not go for transformation. Instead, we will be using some formula that we are already familiar with from fourth semester. In fourth semester, actually, we have, I still believe I covered it in your batch, the World's equation. The World's equation actually is used to calculate the expected value and the variance of a special number of sum of sequence. A special sum of sequence we want to know. And what is that? Say we have one IID random variables, x1. Okay, let me stay with the definition. y1, y2, up to yn. Now, when we actually, and this one is, let's say, y. When we sum this one, usually we consider n as a constant. We use the World's equation when actually n is a random variable. Now we want to, what y represents to a sum of random number of random values. So it is the sum of random number of random values. And the very same thing actually is occurring here. We are summing some IID random values, yi's, and how many such values are there? Exactly n of t, that is given by the Poisson process. Based on the World's equation, what we know that the expected value of y, since here we have two random variables, these random variables are IID, they have the same expected value, which in many cases we represent by E of y or something like this. So to separate this one, let's consider this is x. So E of x will be then expected value this one, And how many such expected values are there? N. Since n itself is a random variable, we'll have the expected value of n multiplied by the expected value of the IID random variables. So that's what is the uh, expected value of the sum of random number of random values, and the variance of such things. It's the variance of x actually is here. Variance of x can be calculated by using this formula. We will not actually explain it. I don't think we discuss it or we derive it in the fourth semester as well. Just it will be with the question, or you can recall it. This is actually the expected value of n multiplied by the variance of x. Then the variance of n is multiplied by the square of the expected value of x. So, actually, here one variance, one expected value. Here one variance, one expected, the other variance and other expected value, but only difference is in the second case, the expected value of x, that is the IID random variables, are squared. If we put this one here in this equation for this compound Poisson process, which actually is x of t is equal to, here we have n of t, the Poisson process, I equal to 1 to this one, yi. Then if we relate these two things, bracket is missing here. So the expected value of x of t is, according to this definition, expected value of this one, n of t. What is the expected value of n of t? N of t itself is a Poisson random variable. Number of arrival up to t is a Poisson random variable, and its expected value is lambda times t, if we measure it for time t. So it is here. These are IID random variables. So their expected value is E of y. So we can easily calculate the expected value of x of t, the compound Poisson process. Now the variance of the compound Poisson process actually is a bit difficult. Actually, it is associated with more parameters. What will happen? First quantity is expected value of n. Once again, sorry, this equation actually is not here. I did not complete it. This one will be sigma square will be expected value of n, which is lambda t. Then the variance of y. From here, variance of y will be sigma squared y plus expected value of x. Expected value of x actually is, for now here, actually it is the x means the IID random variables. So we will have expected value of y squared, then the variance of nt, the variance of n of t squared. So this will be the ultimate equation for calculating the variance of x of t. There is a very good example I found in your book. Customer arrive at a grocery store in a Poisson manner at an average rate of 10 per hour. So we have already one quantity with us, that is, for the Poisson process, the customer arrival of the customer is the base Poisson process, and the amount of money that each customer spent is uniformly distributed between this. This amount of money spent is independent, we need to assume here, otherwise there will not be IID, uniformly distributed. That is what makes the original Poisson process a compound one. So we have the given value of lambda equal to 10 per hour. If we focus here, then lambda is there. And what we want to do, average total amount of money, that means we want to calculate E of xt in an interval of 2 hours. That means we have t equal to 2 hours. Now, what is the variance of this total amount? So we need to calculate both the expected value and variance. Now, to calculate the expected value and variance, what we need the expected value of the IID random variables. the variance of the IID random variables and the value of lambda and t. Why so? This one actually, since it's Poisson random variable, its variance and actually expected value are same. So this quantity can also be replaced by lambda t. So only two quantities that we need to extract from here are the sigma y square, that is the expected variance of the IID random variables. The IID random variables is y. What is the distribution of y? Y is uniformly distributed in between 8 to 20, right? 8 to $20. So what is the expected value of y? For a uniform continuous random variable, it will be the sum of a and b divided by 2. So 8 plus 20 divided by 2, which will result in 14. And the variance of sigma y square will be, I guess, b minus a whole square divided by 12, which will be 20 minus 8 is 12. 12 square by 12 is equal to 12. So if we come back here, that we can easily calculate expected value of the random variable x of t, that is taken from the compound Poisson process x of t. It will be lambda t times e of y, which will be lambda t is lambda has a value 10, t has a value 2, and expected value of y is 12, which will be some values. And the variance of x of t will be lambda t 10 times 2 times variance 12. I made a mistake.
So
So
E of Y 14 হবে।
no one is following me, I guess. Anyway, you are here. Thank you very much. So it will be 2. Then this variance will be 12. And then the square of the expected value will be 14 square. And lambda t will be 10 multiplied by 2. So following the book, the results are actually 280 and 4,160. So here we have 280, 4,160. This is a very good problem in the sense, actually, in many cases, we need to calculate such thing, random number of random sums. Yes, sum of random number of random values. In many cases, we need to do this. So in many modeling, we might need it. So this is a very good one. But one thing that you need to understand is that the beauty of the problem in terms of actually exam, one quantity is fixed for this course. This n of t is always a Poisson process. Since the n of t is a Poisson process, so delta t is always there. The expected value of n of t and the variance of n of t is lambda t always. However, y, I, r, IID, it can be any random variable. Okay, it can be any. It is not necessary that it will only be uniform. It can be exponential. Anything. It can be even Poisson. Here, for example, if we go back here, the number of books that a student buys can be any random variables. It can be binomial, any discrete random variable. Then Pascal, Poisson, hypergeometric, many things. So any questions here? Okay. Now we want to focus on combinations of independent. This independent is very important here. The Poisson process should be independent. What do we mean by the term combination? The word combination here is used to represent the case where actually we have a number of Poisson processes. Somehow we want to combine them. If we combine them, then we actually create, from a set of Poisson processes, we create a single Poisson process. In many texts, you will find the term merging of Poisson processes. That means a number of Poisson processes are merged together. You will also find the superposition of Poisson processes. So whatever name we actually call it, ultimate thing is that we actually combine, we actually join together a number of Poisson processes, or at least more than one Poisson processes together. Question is, what will be the resultant Poisson process? The very first thing and the easy thing is that whenever we will merge Poisson processes, the resultant process will be a Poisson process. If the individual Poisson processes are independent. No need to be identical, but they need to be independent. Here we will consider the case of two Poisson processes that are combined together, merged together to create a new Poisson process. So for definition, we'll consider x of t is the first Poisson process, y of t is the second Poisson process, and n of t is the resultant Poisson process. So you can say n of t is the summation of x of t, and the total number of arrival in n of t will be the sum of x of t and y of t. So the process is very simple. Here you have a Poisson process x of t, another, sorry, my mistake, another Poisson process y of t, and then the first Poisson process has a rate lambda of x, second Poisson process has a rate lambda of y, and we want to combine these two into a Poisson process n of t, where n of t actually is the sum of x of t plus y of t. Now, question is, very first question is, what will be the resultant process, nt? Is it still Poisson? The answer is yes. So if we merge independent Poisson processes together, then the resultant process will always be a Poisson process. This is a good thing. That second thing is that what will be the rate of the resultant Poisson process? If the rate of this one is lambda x, this one is lambda y, then what will be the rate of the merged process? Actually, you can consider in case of this is this we can consider it's a community center. What happens here in the community center? Actually, there are individual arrangement for the female and male guest. So at the time of leaving the community center, let's say male guests are living at a rate lambda x, female guests are living at a rate lambda y. So, and this actually, these community center, actually, this point, the combined Poisson process actually is the, so not the combined Poisson process is the get. So here, as I already mentioned, that merging Poisson processes resulted in another Poisson process. So at the gate, we will have a Poisson process. Now, question is, what will be the rate? Intuitively, we can say if the male guest is coming at a rate lambda x and the female guest are coming at a rate lambda y, then actually at the main gate, the rate of human being, people will be definitely lambda x plus lambda y. That's the main idea of the merging of Poisson processes. Before we actually focus on why the total rate is lambda x plus lambda y, it's very silly. You can check it in your book. But the opposite of this process actually happens when actually people enter into the community center. When they enter into the community center, the flow actually goes in this direction. Male and female guests are coming as a Poisson process. With a rate lambda. And at this very point, they are actually divided. They split. One group go to the male area, and the next group go to the female area. And let's say it depends on whether a guest is a male guest or female guest. Let's say probability is P that P fraction of actually guests are male guests and 1 minus P fraction of guests are female guests. So this is the completely reverse scenario where actually instead of merging Poisson processes, what we do, we split a Poisson process into a number of Poisson processes. And the outcome is that each of the individual processes now are Poisson. Second thing is that what will be the rate of this Poisson process? Since the ultimate rate is lambda, the rate here will be, arrival rate will be lambda p. And here it will be lambda times 1 minus p. So for both the two processes, whether for two cases, whether we combine Poisson processes whether we combine Poisson processes or we split Poisson processes into a number of Poisson processes, in both cases, the output processes are Poisson processes. And once we know that the output processes are Poisson processes, then actually we need to know what are the rates of individual Poisson processes. The fractions actually defines the individual Poisson processes. Okay. Now, here is the subdivision of Poisson processes or splitting of Poisson processes. We'll go there later, but for now, let us see this one. What is it? It says that it proves two things. One is that NT really is a Poisson process, and it has the rate lambda, which is the sum of the individual rates, lambda of x and lambda of y. So how can I do this? Actually, this probability identifies that there are zero arrivals in a very, very tiny time period after t. So it is t, the process starts at time 0, and we have actually t plus del t here. And what is the probability that we have zero arrival in? That is, no event occurs during the period t to t plus del t. Del plus, we have zero arrivals. So this one actually is now to be zero arrivals here, what we need to do, we need to consider the individual Poisson processes. The first one is x of t, and the second one is y of t. Since these two processes are merged to form the ultimate Poisson process n of t, any arrival in x of t will be considered as an arrival for n of t, and this is also true for y of t. So to be no arrivals in between 0 to t, so to satisfy this condition, no arrival in 0 to t, what we need for nt, what we need, no arrival for x of t in 0 to t, and no arrival for y of t for the interval 0 of t. So since both of these two are required, that means both of these two should happen to have this event to occur. And that's why the probability will be the intersection of these two probabilities, and that's why we need to multiply them. Probability that x of t plus del t minus x of t, that means zero arrival in the interval 0 t, it will be 0, and this one will also be 0. Now, as we have discussed in today's class, this probability of zero arrival is represented by this way. After some simplification of these two product of these two equation, what we get, which eventually reduces to this one. So one thing that we understand from here, that this is same as the probability of zero arrival for the Poisson random variable. So we conclude that and t is a Poisson process. Furthermore, from here, actually, we also conclude that this process has the rate which is sum of the rate of the two individual processes lambda. So we can conclude when we merge two Poisson processes with rate x of lambda x and lambda y, then their merged process, resultant process, is also a Poisson process with rate lambda equal to lambda x plus y. Now, let us assume that L of x and L of y denote two very important quantities. What are these? Time until the first arrival of both processes. So L of x is the time until first arrival occurs in process x of t. Today we so L of x actually is the time that is required by the process x of t to have one arrival, the first arrival. Similarly, L of y. So to identify the distribution of L, we actually consider these two. What is the probability that L of x is greater than t, or L of y is greater than t as well? Then from these two, we will calculate the probability that L of t. So once we have this one, then we can have the CDF of L. What would you? The probability that this one actually is the probability of their individual, because they are independent. So this probability will be, so here if we focus, where? X of t. So to have no arrivals before t for the resultant process, what we need to ensure that there will be no arrival before t for the first process, and no arrival for the second process as well. So the probability of occurring that to the product will guarantee that there will be no arrival for the resultant process. And this one we already have seen that it is e to the power lambda x time t. This is e to the power lambda x minus lambda x time t, and both cases minuses are there. So we can simplify this one. So lambda is equal to lambda n is the rate of the merged Poisson process. So from here, actually, we can calculate the distribution of the time that is required by the merged process to have its first arrival. So we already discussed about this one. Now let us move on to comparison of first arrival times of two processes, two independent Poisson processes. What does it mean? We have two Poisson processes. One is, let's say, x of t. Another one is, let's say, y of t. Then we have rates of these two processes, lambda x and lambda y. And these two processes are independent Poisson processes. What we want to find out? We want to find out the probability that the first arrival of xt, let us denote it by lambda, tx, occurs before that of yt. That means before any arrival occurs in the process y of t, the first arrival occurs in the process x of t. So the first arrival of process x of t occurs before the first arrival of the process y of t. Note that these two are independent exponential random variable. You can recall the first arrival time of an exponential, of a Poisson process is exponential random variable. And since the two processes are actually separate, they are identical as well. They are by no means affecting each other. Now we can calculate the PDF of Tx, which is exponential. We already know the interval times of a Poisson processes our Poisson processes are exponential, then we can calculate the PDF of the PDF of the PDF of actually Ty. This is also exponential. And what is the joint PDF of Tx and Ty? Since they are independent, their joint PDF will be simply the product of their individual PDF. So these two variables are taken at the beginning, lambda x times lambda y, then e to the power lambda x, e to the power lambda y. So what we get the joint probability. Why we are calculating the joint probability? We are calculating the joint probability to understand one thing, that is, we want to calculate the probability that this one. To calculate this one, their joint behavior is necessary. We need to know the joint. Let's say in this direction, we have the t of x, the time taken by the process lambda x to get the first variable. And in this direction, we have ty. So tx is the time that is required for the process x of t to get its first variable, and ty accordingly. This line says both the processes have their first variable simultaneously, because this line is ty equal to tx. And any point above the line here, ty is larger than tx. Any point here, tx is larger than ty. On the line, both are same. So for all values of x, we want to calculate this area. So all values of t of x. So because this area is the place where tx is less than ty. And if we multiply this area by their joint probability, then we will get the PDF or the probability of this one. And to do this simple formula is used. Only challenge is this one actually is bounded by this area. The math does not tackle the probability. Rather, we actually calculate this probability by considering this is the area for which this condition actually is true. That's why what we do, we multiply the joint probability for this area. And how we do that? The joint probability is multiplied with the area, and area actually is calculated by the Tau integration. Question is, what will be the limit? X will go from 0 to infinity, because this condition should be true for all values of x. And y? If you focus here, for a particular value of x, y will be from x to infinity. That's why the limit of x is 0 to infinity, and the limit of y is x to infinity. After that, it is very silly thing we found. So one very, very important property actually is this one. It helps you solving many problems. It helps you to make many problems at the first glance that are looking very complex will become very easy. So, and definitely this is very important for our course, right? So let me recap it is this. If we have a Poisson process x of t and another Poisson process y of t here time, then if we assume that the time that the first process x of t requires to have the first arrival is tx, and the second process requires ty time, to have the fast arrival. You can consider that the just a minute. Close WhatsApp still. Okay. So we want to know that the probability that Tx is less than Ty. So the problems have been formulated in terms of two independent Poisson processes. However, if you look very closely, you will find that it is the relationship between two independent exponential random variables. So what we conclude from here, this formula is not only applicable for two Poisson processes for their first arrival time, comparison of their first arrival time, but also it is applicable for any two exponentially distributed random variables if they are independent. So any two independent exponential random variable, this formula is applicable. Okay, and we can calculate many. Okay, here is a very interesting. Okay, no, we will go serially. Let's go serially. The memoryless property, then we will actually learn some memoryless property. Before actually starting the real problems that are associated with this chapter, we have a lot of theories. Okay, we will solve the problems in the next class, inshallah. So what is a memoryless property? We call a person memoryless if he forgets past things. There are random variables that forgets their past history. So such random variables actually are called memoryless random variables. I can recall in fourth semester, we talked about memoryless random variables, and at the time we told that there is one random variable in the continuous, among the continuous random variable, which is memoryless, as well as there is another random variable which is also memoryless. Can anyone tell what are these two random variables that are memoryless? One actually from the continuous, among the continuous random variable, another one is among the discrete random variables. Anyone can recall?
The
Sir,
exponential.
exponential.
Okay, so exponential is memoryless, and among the discrete, very good.
Sir, geometric.
Why?
Sir, if we replace the so for example, if we have a box with three red balls and two green balls, if we pick one and then replace it immediately, then the previous outcome does not affect the next one.
For example, you pick 10 balls and you count number of red balls, say 5, 6, whatever, and you return all the balls, and again you pick 10 balls, you may get 5 balls or you may not, right? They are independent, right? So, but here the number of successes actually are the binomial random variables. So are they memoryless? Just for discussion, are they memoryless? Actually, the memoryless is thing that actually forgets events that occurs past, right? Actually, most of the cases, actually, we consider that it cannot keep track of time. Consider a light bulb. The expected lifetime of a bulb is 6 months. Say, after 6 months, what is the expected lifetime? It still remains 6 months because the bulb cannot actually remember it already has served for a period of 6 months. Okay. Now, actually, in reality, there are situations where actually random scenarios, random things are memoryless. For example, let's say this is a bus stop. Person A arrived here to catch a bus. And let's say he is expecting that the probability that he is actually time to catch the bus will be greater than 5 minutes. So this is the complementary CDR. Now, it is not guaranteed that after 10 minutes the bus will arrive, right? It has some probability. Let's say a value, A. Now, after waiting 10 minutes, person B joins him. Now, person B at this very time point, B, and if we consider A here, already 10 minutes is passed. 10 minutes actually, not 10 minutes have been passed. And now here, this person B joining here, he has a probability that the bus will arrive after 5 minutes. Now, this probability for person B and this person A, they are going to catch the same bus. The probability for person A that X is greater than 10 plus 15. And let's say for person B, it is Y or X, whatever. Since X is greater than 5, are these two quantities same? The probability is same? Is the question clear?
Sir, can you repeat it?
At this very point, person A has already waited 10 minutes and waiting for a bus, a specific bus. Person B joins here and actually will catch the very same bus. So what is the probability that after 5 minutes from here, the bus will arrive? That means for person B, what is the probability? Let's say the time actually is X. After X minutes, the bus will come. The probability that X is greater than 5. This is for person B. But person A is waiting from here, point A. That means if we consider this length, what is the probability that for person A, the waiting time will X will be greater than this 10 minutes and these 5 minutes. That means X will be greater than 10 plus 5. My question is, are these two probabilities same? That means X is greater than 10 plus 5 and X is greater than 5. Intuitively, if we are standing here, then the bus will arrive after 5 minutes. So the probability should be same because person A will catch the bus and the person B will catch the very same bus. They will use this same bus. So from this point of time, the probabilities should be same. However, for person A, this probability is this one. For person B, this probability is this one. To make it right, what should be the case? If the probability of X is greater than 10 plus 5, given that X is already greater than 10, that means you already wait 10 minutes, should be equal to probability that X is greater than 5. Only then actually these two are same because this one will reduce to this one, and to reduce to this one, actually this person A has to forget that he has been waiting for the past 10 minutes. They are on the same page now. Here, they need to wait with the same probability for 5 minutes for 10 minutes, there will be different probability, but same probability. And to be these two conditions true, what we need, this one should be equal to this one. And we write this one. Probability that x is greater than s plus t, given that x is already greater than t, is equal to x is greater than s. That means this person who has been waiting for 10 minutes here, he has to forget it. And by this way, actually we say if this condition are true, this condition is true, then the random variable x should be memoryless because it can forget. The waiting time does not affect the probability for any future time, right? But in reality, the other thing is that if you are waiting for a long time, the chances are higher to get the bus. But Poisson says that whatever time you have been waiting for doesn't matter. Probability will only depend on the future time. And this equation can be reduced to this one, which means that we apply the rule for conditional probability, which is probability of A and B divided by probability of B. Here, I'll take 5 minutes more because at the beginning, actually, I could not start. Only 3 or 5 students were there. And I don't think you have a class now. But if you have a class, another is rescheduled, then we can stop at 3. Otherwise, I want to take 5 minutes to finish this one. So what happens? This is the definition of the conditional probability. And this conditional probability of A given B is the joint probability of A and B divided by the marginal probability or the probability of B. Same thing is that we can consider this one as event A, this one event B. So the joint probability of event A, which is x is greater than s plus t, and the event B, which is x is greater than t, divided by the marginal probability. Now, this joint probability x is greater than s plus t and x is greater than t. So we will actually take the intersection of these two events, right? This one is one event, this one is another event. Can anyone tell among these two, what will be the intersection of these two events? This one or this one? X is greater than s plus t will be the intersection of these two events, or x is greater than t will be the intersection of these two events? Any volunteer here?
Answer x greater than s plus t.
Okay. Any other? Actually, this will always confuse you. Now, let me draw a line. Time starts from here, right? 0. We have point t, and this one is s plus t. When we consider x is greater than s plus t, then it starts from here and goes up to infinity. When we consider only x is greater than t, it starts from here and goes up to, and their intersection will be, this one is x is greater than t, right? And this one is x. And this one is x is greater than t. So the intersection will be x is greater than s plus t or t plus s, right? And you are right. Okay. So in many cases, we consider that x is greater than t and s plus t. This is t is smaller, so it should be here. So the intersection will be the x is greater than s plus t. And so we can rewrite this equation as probability that x is greater than s plus t divided by probability is x is greater than t equal to probability that x is greater than s. And what we can write, probability that x is greater than s plus t equal to x is greater than s times probability that x is greater than t. Any random variable any random variables that satisfy this equation, we call that random variable a memoryless random variable. If we focus here, probability that x is greater than s plus t, we need to prove that x is greater than x plus t. We see that it is true for a geometric and exponential random variables. Today we'll see it is true for the exponential random variable because this is the complementary CDF. So 1 minus the CDF. And we know for exponential random variable, the CDF is this one. So we can write this 1 and 1 can cancel out each other, e to the power lambda s plus t. We can actually split it, e to the power lambda s and e to the power lambda t. So following the same, we have been seeing since the beginning of today's class that the complementary CDF x is greater than s is e to the power minus lambda s, and probability that x of x is greater than t is e to the power minus lambda t. So since this condition is satisfied, we say exponential random variables are memoryless. There is one more thing we call a fresh start property. The Poisson process, which actually consider the number of variables, counts the number of variables. If we consider that time t is here, then here actually we have one Poisson process, say at time Poisson process arrival x1, x2, x3, and so on up to t, and then here x t plus 1, x t plus something. What happens? Starting from any point of time, the past process, past stochastic process, which is collection of random variables, are independent from the future of the process due to the independent increment and stationary increment property as well. So what happens? Future state of the process after any time are independent of the past. These are the states. And from that point of time, the process actually behaves like a new process. That's why we call, starting from any time point, we can have a completely new Poisson process, which actually we term as a fresh start property. The Poisson process can start from any point of time, from any point of time. These two, memoryless and fresh start property, actually gives us a very, very, very powerful tool to solve many of the problems very easily associated with Poisson process. By the memoryless property, we assume that the past of the process is forgets. The probability only depends on the future time. Mainly, we are focused here time. Second one, the process can start at any time. So starting from here, we can consider this one is a new process. So you can set a time and you can actually ignore the past. You have a already new process and you can consider this one is a fresh Poisson process. That actually gives you the fresh start property. So we will stop here. Thank you for your patience. If you have any questions, we can discuss. Otherwise, thank you very much. Any
Sir, for
Yes.
the problems of these concepts, will it also be in chapter 5 of Ross?
Yes, in the book you will find. I will upload the lecture today or tomorrow, inshallah. Okay, this one. You already got the first two chapters, right?
Yes, sir.
Now, from this knowledge, you can be able to solve almost all the problems, or many of the problems, majority of the problems in chapter 5 of the Ross book. Okay, you can start trying. And we did not solve actually many problems so far, only one related to the compound Poisson process. And we will solve the problems in the next class. 4 or 5 problems we will solve, hopefully. Any
Okay,
questions?
thank you, sir.
Okay, thank you very much.